In this video I will explain to you what the mesh current method in network analysis is and how you can use it to quickly and easily compute the unknown currents in electrical networks and circuits you want to set up. We will go through an example step by step here in this video, and I will explain what the so-called virtual mesh currents are all about and what you can do with them. And finally I will also compare the method with the branch current method, which we have looked at in the last video. Now let's quickly review some things which we need in order to understand this video properly. Firstly, the determination of currents and voltages in networks is one of the fundamental tasks in electrical engineering, and it ensures that all components can properly operate as they should be, that not too much energy is invested into a single component, which then might be damaged. And in the last video, we have already learned about the so-called branch current method, which uses Kirchhoff's laws and Ohm's law to set up a system of linear equations, which help us determine the unknowns in the system and which we can solve using the standard methods such as, for example, Cramer's rule or the Gaussian elimination rule, for example. And in this video, we're going to describe the mesh current method. We will look at how it works, and the bottom line is that this method requires fewer equations and provides faster results than the branch current method, which is especially useful when you compute it by hand, for example, in an exam situation. Let's look at the overview of the method. Firstly, the mesh current method differs from the branch current approach in that the node rule is not used. It has higher practical relevance because it's computationally more effective, and the learning effect is still good here simply because it allows you, it gives you some insights into the inner workings of a network. Now let's look at an overview of the method. The basis of this approach is to set up mesh equations for all circuit parts in which you want to determine unknowns. So you do not necessarily have to solve the entire network, but you have to include all the circuit parts in which unknowns need to be determined. And in contrast to the branch current method used so far, we will use this concept of virtual mesh currents, which we have not used in any of the methods we have looked at before. So let's take a look at what virtual mesh currents actually are. Now, before we do so, again, the same circuit as we have used before. Two voltage sources, U1 and U2, three resistors here, and the approach or the task which we are setting out to accomplish here is to compute all the currents in the network here. There are three of them, I1 entering through R1, I2 leaving, most probably leaving through R2, and then R3 entering or leaving, we do not know yet, into this junction point here. So two ideal voltage sources and three resistors. Now the first step in this mesh current method is to set up the mesh equations. And firstly, the current directions in all branches with unknowns, they need to be assumed in an arbitrary manner. So we can simply assume how the current might flow, and this results in voltage counting errors for resistors and sources. So let's assume the current flow, or let's assume the circulation which we are performing here is performed in a clockwise manner, both on the left and both on the and also on the right. And then we can set up this loop equation here on the left: minus U1 plus UR1 plus UR2 equals 0. So that's the loop we are going through here on the left side. We're going to do the same on the right, which yields us this equations. So the meshes we have formed now capture all the unknowns which we are looking for, even though the unknowns are not yet present, because we first have to replace them using Ohm's law. But this is something which we're going to do in the next step. For now, the equations we have are simply the voltage equations, which equal to 0 according to Kirchhoff's second rule. Now, second step is to adopt a so-called virtual mesh current. And in contrast to the branch current method, which we have talked about in the previous video, we now assume that a separate mesh current circulates in each mesh. This is virtual because obviously you do not have a current circulating through the left mesh, which is identical at all places, IA in this case, and neither do we have an identical current circulating through all of the right part, simply because we have learned and justified that currents branch at junction points. So this is a virtual assumption, but it's not allowed to violate the rule of physics. We are only assuming it for the sake of reshaping these equation here to enter the unknowns. So the left equation here, minus U1 plus UR2 plus UR1 plus UR2 equals 0. This is the first one we're going to use to introduce these virtual mesh currents. Let's start with R1. When we replace UR1 with using Ohm's law with the product of current flow and resistance value, we are using IA to replace this this property here. So R1 times IA. We are assuming a mesh current called IA. Then R2 is a little bit more complex because we have actually two currents flowing through it. The one from the left mesh, that's the interface between the two meshes. R2 is the interface between the two meshes, which connects the equations. And firstly, we are going to count positive IA entering through R2 from the top, and then we are counting negative IB, which comes from the bottom. And the direction of counting is determined by the mesh we are considering. So for now, we are considering the left mesh, which is counted clockwise, and then in clockwise direction, the green arrow is positive and the blue arrow is negative, which is why we have minus IB here at the right side. And this equals to 0. We can do the same for the right mesh here in the lower equation. So U2 starting from this source here, then plus R2 times IB. IB is counted positive this time because we are also moving clockwise and we are moving into the direction of the blue arrow here. And then we are moving against the direction of the green arrow from the other mesh. This is why we're counting it negative here on the bottom side. Plus R3 times IB. This is obvious, again, Ohm's law to replace this arrow here. So we now have inserted the unknowns, but please consider here that we now have reduced the number of unknowns actually, because we have 3 unknowns, I1, I2, I3, and now we have only 2 in this equation here. Only the 2 virtual currents, these are the unknowns which we have entered here. IA and IB are the unknowns for this network, and we have 2 equations, 2 unknowns. This looks pretty good in order to solve it using a linear system equation solver. Which is exactly what we are doing here on the next slide. So we are now reshaping these equations in the same way as we have done it in the branch current method. We are separating the factors from the unknowns. Unknowns are IA and IB. And if we are separating the equations from the previous slide in a way that we have R1 and R2 separated here, then we can say this is the factor of IA in the first equation. IB has the factor of minus R2, and it also results in the result U1 here on the right, which gives you the first line in the linear equation system. So if you enter the values given in the network, R1 plus R2 results to 6 ohms, R2 or minus R2 results to minus 2 ohms, and U1 is 28 volts, which is what we enter into this result vector here. We do the same for the bottom line here, and this results in this vector here, x1 equals 5 amps, x2 equals 1 amp. This is not yet the solution to the tasks, so do not stop here, because this is only the solution to the virtual mesh currents. We have to recompute or retransform these mesh currents into the actual real currents we are looking for. So IA also circulates here in this left part of the network, which is identical to I1, because I1 also circulates here. So I1 equals IA equals 5 amps. I2 in the middle is the difference between these two virtual mesh currents. So IA minus AB, 5 amps minus 1 amp is 4 amps, and I3, similar to I1, is simply the current IB, which circulates in this right part of the network. So this is 1 amp. So this small transformation step here, which is based on basically Kirchhoff's rule, Kirchhoff's first rule, this gives you the equation or the results we are looking for. And the advantage is that the linear equation solver here has less work to do. With such a small network, it's not that big of a deal, because it could just as easily have solved a network with 3 unknowns, but imagine a much more complex network with many dozens or even hundreds of components. then reducing the complexity of the network. And also, it's not only -1 equation. The advantage is increasing a lot if you enter more equations or more components into the network. So we are really reducing the complexity of the network analysis problem here by a large extent by transitioning from the branch current method to the mesh current method. Now let's compare it to the branch current method a bit more formally. It's very similar to the branch current method. We are using Kirchhoff's first law to set up mesh equations. However, the difference is it's assumed here that a so-called virtual current is circulating in each mesh, and in branches where meshes overlap, the virtual currents are simply added up, just as we have done so in the example. Now, as I talked about on the previous slide, the number of linear mesh system equations is smaller here than with the mesh current method, which makes it computationally more efficient. And this is especially prominent for larger networks. So one new item here, which I have not yet shared with you, this mesh current method is particularly well suited for computing a very important circuit in electrical engineering, which is called the Wheatstone bridge, which can be used to evaluate sensor measurements, for example, a light sensitive sensor or a temperature sensor. This is usually done with a Wheatstone bridge, and by using the mesh current method, we can very easily arrive at a solution to this Wheatstone bridge problem, but more on this in a later video. So in conclusion, we can say that the mesh current method is a much better choice when it comes to network analysis. That's all for this video here. I hope you enjoyed it. If you have any questions, drop me a comment down below and I will try to help you as best I can. And now I wish you a nice day. See you next time here on The Fearless Engineer.